Yeah, been a lot of stuff happening in the news as well. So
Yeah.
yeah, pretty scary. But anyway, um, let me just share my screen, and we'll just pick up where we left off last week. Uh, so yeah, we were looking at the absenteeism at work and trying to get that into some sort of manageable data set. And I found that I think if we like at the end of last week, I think I didn't know. I wanted basically a matrix kind of data structure, and I didn't know of one in F sharp, but I had a look around later afterwards, and there's this thing here called array 2D. Can you guys see my screen? Sorry, I should
Yeah.
change. Yeah,
Yes.
yeah. So it turns out there's this 2D array module that you can use to give you slices and of rows and columns. So I thought I'd use that. So I took a few parameters or few attributes from the data set. I think I've got 7 here. So absenteeism, time and hours, the age, body mass index, um, and some other attributes, and that all gets packed into a two-dimensional array. Then I did some work afterwards just to normalize it. So this here normalize it generates a new array from the old array. So you've got the old array here with the data in it, and then the normalize function just takes each column. So I use the slicing syntax here to do it. So if you look up, I mean, I think you guys are familiar with R and stuff. So R will have a similar ability to slice columns and arrays and rows. Sorry, slice rows and columns. Uh, so yeah, that just says give me the column at there with all the yeah all the elements in the row at the ith column, and then because we want to normalize, um, make sure that each attribute is value in each attribute is bounded between 0 and 1. So that's why we normalize it. That's what I do here, and then I create the normalized data data matrix. Let's call it a matrix because that's really what it is. And then because it ends up being transposed, it ends up needing to be transposed. I wrote a transpose function here just so that it comes out in the right order again, and you'll see what I mean over here. So this is the original data set. This is the original array. So those are all the values of like. So for this person in this row, his absenteeism time and hours is 4. His age is 33. BMI is 30. Service time would be 13. Workload average per day is 23954. He's not a social smoker. It's a 0 here. And the last is transportation expense. And then for the second person in this data set, we can see that he's never been absent. His age is 50, BMI 31, and service time 18, whatever that is. Workload is 239.554. interestingly, that all these workloads are the same, which is sort of what you'd expect. If you look at this column, I mean, they're all, let's say they're all doing the same job, they'll be putting in the same number of hours. So when you're reading in data and looking at your data, you can cross-check it with something you already know or what you expect to be true. And so that gives you confidence that what I'm reading out here is mapped to the right values here. But anyway, that's the first array read in over here. And so we want to normalize this. So we want to bring all of these values down between 0 and 1. So that's what I do. That's what happens in the next step. So normalization takes, so it'll take 4, 0, 2, 4, 0, 2, 4, and 2, and normalizes it. So you've got the normalized values here in this row, and they're the normalized values of this. I can't highlight by column, but it's this first column here. I don't know if there's a drawing tool, and there's annotate. Let's try this annotate draw. Yeah, so I can try this draw. So yeah, so I can do something like this. So that column there is normalized here. Do you see those lines? The square boxes they've drawn?
Yeah.
Yeah, okay, good. No, you could do that. Okay, so they're all drawings. There we go. And then transposing this because we need to get it back in the right order again. So do the transpose, yeah. And so you can see, where was I? Draw boxes. So this normalized column row here just maps down here, and same for the next column and the next column. So this is the transpose. So it's just in the right order again. So once we've got it there, I think then now we've got the data sort of cleaned and prepared for doing the kNN thing. So now I have to remind myself how kNN works. I think it's each let me just have a quick look. I've forgotten. Oh, what do you think it should do next? Probably throw this question up to you guys. So, any ideas? Yeah.
I'm not sure.
Yeah. Yojith, do you know what we should try and do next for the kNN algorithm?
I'm not really sure. I think I didn't hear a bit of it for a second there, so I didn't quite hear the question properly. But
Oh, okay. I was just wondering where we should go next. Like, um,
I'm not really sure. I'm not as familiar with kNN as I am with some of the other algorithms.
Okay. I sort of have an idea what we need to do. I was just wondering if you guys could help me with it. Essentially what we have to do is calculate a distance between the test data and each row of the training data. So once we get that distance measure, we can say, okay, for like so in this sample example here that I have, I've got how many rows? I think I've got 5 rows. So assume this is the training data. I've got 5 rows. And say I want to classify another row and find out, like, is this person a social smoker or not? So what you do is you calculate the distance between this row and the given test data row, and then you do it for the next row, and you get another distance value. You do it for the next row, you get another distance value, and so you'll end up with 5 distance values. And then you find out which one is the smallest. Or you take k, like what they do is the k is the number of you sort it first. You sort all those distance values, and then you'll take the top 5, say, and that's your k value is 5. You'll take those five values, and you'll see where you look at those rows, and say you're looking for social smoking. If all 5 of those happen to be closest to this data point that we've tried, and all 5 of them are social smokers, then you can assume that this data point is a social smoker as well. If 3 out of those 5 are social smokers, then because it's a majority, you got three are social smokers and 2 aren't. You can say that your data point is is also a social smoker. So does that make sense?
Yeah, that makes sense.
For
Yes.
kNN,
Yeah.
that's the algorithm as I understand it,
Right.
or the idea behind it. You basically just, like, I wonder if I can draw the like, it's kind of like drawing it makes it kind of easy in some ways to see what's going on. But say you have let's draw some other things here. So let's say we have that red represents someone who's a social smoker, say, and they cluster around here. And we take another color, and well, maybe not blue, but green stands out a bit easier. Greens aren't social smokers, and they just tend to cluster a little bit on this side. And then we have our test our person in question. We don't know the person. We don't know if this person's a social smoker or not. But we've got all these other attributes that we know about this person. And when we calculate, and say, like, he lands up there with, because what these rows are, it's just a multi-dimensional vector, or it's just a bunch of dimensions. So because I can only draw in 2 dimensions, I've only got 2 attributes. The two-dimensional drawing is essentially just two vectors, right? So you've got you can call them I and J columns, say. So when I draw, what I draw here is it only corresponds to a data set with 2 attributes. But we're working with a data set with I think 7 attributes I have in here. So it means that you have to imagine that you're working with a 7-dimensional entity, right? That's essentially what's going on. And when you're calculating the distance value, you're calculating that distance in 7 dimensions and using 7 dimensions, not just 2. But in this drawing here, I'm doing it in 2 dimensions because I can only draw in 2 dimensions. But anyway, what's going on is that the algorithm it's just computing distance values. So it's taking the 5 closest point. Say the k value you pick is, for argument's sake, is 5. It's computing the closest points, let's say. I'm visually just guessing. I may be a bit wrong here, but I've got 1, 2, 3, and maybe it's this one here. So it'll actually calculate the distance from it has to know the distance. It has to do it for all the data. So the first run of the algorithm will be to calculate the distance from this white dot to every single other dot on in the space. So it'll do that for everybody, and then once that's calculated, it'll pick the closest values, the closest ones, and just visually, I'm assuming by visual inspection, I'm just marking these as the closest that I think are the closest. 1, 2, 3, 4, 5. So that's 5 of them. It picks the 5 closest because your k parameter is 5. And then it says, out of these, which ones are social smokers or not? We've got 3 social smokers and 3 non-smokers and 2 social smokers. Therefore, our person in question is not a social smoker. That's what the algorithm is doing. So we have to basically write the code to do that, and I think that's in a way that's the hard part, is getting like it's getting from this abstract idea where I've drawn this diagram and then translating that into actual code. And some people can get it quite easily. Sometimes, I mean, I struggle with some ideas as well. But I think for kNN, it seems fairly straightforward to do. So what we have to do is we have to look at each. Let's get our sample data. Let's just get a row from our data set. So we call it sample. So we have a data set over here, just data. If I can grab it up, let's see if there's a function that basically lets me get something out of it. Rows quite map. Yep. Yep, I think they're about how many in the absentees? Rows are here. Yeah, so there's like 741 rows. So if I just skip up to, I can get the last skip 700. And then I'll have about 40 rows there. So if I want let go person, so grab that. Must be a way to get the row out. That row out. Ah, okay. Sequence.truncate. That'll do. think I've just misaligned this. So, yeah. And maybe we just wait. So let's check that we've got what we want out of this. So that's the single, that's somebody from, I think, the 700th row in this file. So if I look at row 700, should see some of those values there. So where are we? Let's see, 230. So 230, 19, 9, 2, 179. So let's have a look here. Find the first. Where is 179.0? Should be this row, somewhere around here. Let's see. 179.0. Let me find. No, that's not that file. Why is it looking at that file? I'd expect to find some of those values here. 178. Maybe there's this value, and for some reason it turned into 1. Why would it do that though? 23756, 23019. I don't even see a 30 in this row. Let's go find a 19. 19's, but doesn't help me much. I'm just trying to correlate what I pulled out with what I pulled out of the data with the file, just to make sure that I'm getting the right thing. It looks right. I mean, it looks like it's reasonable. I'm just puzzled why 179 is here and it's not in this file. So that's the transportation expense attribute. So if I go to the top and I look at how do I move this? Oh, so look, yeah, it should be the third from the end. No, I didn't. Oh, I see. It's not. Yeah, okay. What's transportation expense then? 1, 2, 3, 4, 5. Like column 6. Oh, here it is. Silly. I was searching for 179. I think I typed 179.0. Yeah, I actually typed the point. I didn't type the. Yeah, okay. So it is there. Okay. So this looks like it's the row with the values. So you'd have 179 to 3019. Those sort of like values that look like they should be in this row. So there's a 30 there, a 2 there, and a 19. And this value is the time the person's worked. 237656, which is their workload average day. Yeah, so that looks right. So that's a single person. Now for each item, and so we've only taken 5. So now what do we call it? Our T training data, say, and then for each row in training data, do um put in with um single person and the row. So that's what we just want to do. Well, want so that distance equals that, and then we want to put that distance into some kind of list or array. Like go list up and distance. I would just make this the whole. Actually, just turn this into a list. Let distance values equal. Let's do this. Build distance. Data is. Why is training data not appearing? Gotta run that so it recognizes that this is here. See what we've done. Flight list, Euclidean work. Do I have it? It's the list, flight list. What do I have instead? Let's row. Oh, we gotta indent that. There we go. And what's row? Training data is an array. Uh, I just make this in array 2D. Sequence. Oh, no. Really? Really me. I keep confusing these two. Two types. Um, row. All the uh, thing like that. People. So this to grab a space as well. So whereas they did here, the transpose. Hmm. Why this is channels? Ah, okay. No, that's fine. Let's map that to a list then. That is row. Oh, the text thing then. Good work. Good the comma. It just takes a bit of like the red underlining is a bit slow, so it's a bit. It should compile, even though even though that bit there was red, it should. I realized that it was just misleading because it's slow to the the ID is slow to update it. So that gives me a list of distance values. So that looks kind of interesting, I guess. Okay. So this says this is the distance of you've got 5 distances here. These are the distances from the original 5 people that we chose, that we created over here. So if I was to finish this off, all I'd do is I'd pick like say, well, let's just say this is the sample we get. Normally the sample size should be bigger. Like I shouldn't just be using 5 people here. I took 5. I should take like 100 or so, and then pick the closest 5. Um, so all it's saying is that to find the one that's closest to us, which I think it's this 137. So 135. This one here is the closest value. So that would correspond to the first person in the set. and if we were actually to print out what our candidate is, single person, dot, value. And then social smoker is the what 0, 1, 2, 3, 4, fifth column. And we check it with our first value here, say this guy, who's the first, he's right here. So the fifth column here is 0, 1, 2, 3, 4, 5 is this one here. So he's not a social smoker. Then we'd expect that because the distance is he's closest to them, he won't be a social smoker either. But if we print that up, we get social smoker 0. So yeah, he's not a social smoker. But yeah, this probably isn't. Yeah. To work on this further, you'd need to actually just have use more of the test data and training data, and make sure that you're getting the right results, in the sense that you're getting results that correlate with what you expect. And that's just that's just work, right? You have to have a look at all the data and just make sure that it's making sense. The outputs, the what you expect it to be. Well, in this case, it's okay, but it's only one sample really, and it's too little to tell if it's doing the right thing. But essentially, this here is your kNN algorithm. I should write that in here. This is kNN. It's this bit here after the normalization. But I haven't sorted it, and I haven't picked the top k values after the sort. Yeah. So yeah, I mean, I think I think it's probably just something to be aware of. That it's often easier to describe the algorithm than it is to actually write it at times. So, oh, what do you guys think? Well, first, did that sort of make sense, or did it help you with your courses, and does it correlate with what you know about kNN?
Definitely help me understand Canon a lot better than I did before. Like on a conceptual level.
Hello,
So that helped.
anyone there?
Oh, can you not
Yes.
hear me? Hello?
Oh,
Hello.
sorry. My speaker went off. Sorry. Uh, I can hear you. I should be able to hear you now. My speaker switches off after no sound. So yeah. So I'll just ask the question again. Does it correlate with what you know of kNN?
Yeah, for sure. Definitely helps me on a definitely helps me like look at how to code it, and like on a conceptual level is pretty useful.
Yeah. Yeah, I'm just hoping that I got the concept level right, because it's not really it's not something I'm familiar with. So
Yeah. Yeah, I had a lot of trouble understanding Canon before, I think. But this definitely helped. So
yeah, I think it's one of the easier. Probably shouldn't say easy, but I mean, what did you have? Let's go into that. What did you have difficulty understanding about it?
I think honestly, I think it was just strange to think about distance as being a sign of correlation between variables. I mean, now that I say it, it seems like a pretty simple concept,
Yeah.
but at the time it was just, I don't know why I just couldn't quite grasp it.
Yeah, I think maybe it's just because you used to think of distance as a physical thing.
Yeah,
Maybe that's
yeah,
all it is.
yeah.
But yeah. The thing is, like, the maths abstracts it a bit. So what people do in maths is they take like a physical concept and then they apply it everywhere. So you see that a lot, that pattern a lot. But it's grounded, the initial idea, it's grounded in some sort of reality in general. So you build out, the way people build abstractions is by looking at specific instances, and they build a general sort of description from that instance, and that's essentially what you're doing when you're computing distance. Like, distance is, we use the word distance to mean a physical, generally in colloquial speech, a physical a physical thing. Like, it's the distance between here and like Australia and the United States, for example. But you can also use it in more abstract sense to say like the distance between uh like two people's values, for example, is quite large. You know, like a lot of religions have different values, and you can say that different people have, like, if you're an atheist versus, I don't know, some other religion, you'd say the distance between your values and that other person's would be quite large. Yeah, so people abstract that concept.
Makes sense. Mm.
That's what kNN is.
Yeah.
Sounds like. Faiza, have you got anything to say?
I think I can totally relate to Yojith as well. Like when I was learning the k-mean clustering, I had the same difficulty understanding how the distance I used to think is not the same as the distance we are uh, doing it. So
Uh-huh.
that's um,
Okay.
it's a different view. Yeah.
Uh, what do you think? How do you conceptualize distance then? Is it simply just because you're used to using distance in the physical sense?
Yes, yes. But I I also took the example that you gave just now about the values. I think I understood the distance something like that as well for the k-means clustering, and that becomes that made it a bit easier, I think. Yeah.
Yeah. I mean, like, I think an easy way to think of it is like, maybe this will probably make sense to explain it like this. Like, say you've got uh say you've got the locations of like 50 cities in the world, or say like 1,000 cities, for example. You've got their locations on a map, right? And then you take a random city. You don't know which country it's in, but you take a random
Yes.
city and you know its location. And so and then you calculate the distance of that random city with all the 1,000 cities you know. And then you take the closest cities, the 5 closest cities. Yeah?
Yes.
And then now what can you say about this random city and the 5 closest cities? Where do you think which country do you think that random city is in?
The one closest to it.
Pretty much, yeah. So that's kNN, right? So it's looking at those K where it's the k is just a number parameter that says I'm taking 5 or 10 or 20 of the closest, and I'm looking for the majority attribute
Alright.
that I want. Yeah. So in this example that I described, you say I've got like I've picked 5 closest cities. If all 5 of them are in the United States, then you can pretty much say off this random city, yeah, it's probably there's a huge likelihood that the city is going to also be in the United States. Yeah, so that's all kNN is really. Like it's just
Yes,
so that's
that
why we
makes
use the
sense.
distance, and we use the distance there, and the attributes in this case are your x and y coordinates of the city. But the thing is, you can extend that into into more dimensions. So x and y you have your graph x and y in 2 dimensions. You can add a third dimension there. So for a different sort of feature set that you want to characterize, or you want to investigate, you can have more dimensions there than 2, and then you use a distance equation. So the Euclidean distance formula that you normally use for 2-dimensional distance, that extends into multi-dimensions for 3, 4, 5, and 6, and so on. And it's just repeating the same squaring and square rooting. So each feature or each column in that vector gets squared, and then that's summed, and then square rooted. The whole thing gets square rooted. That's all it does. But yeah, so that's all. If you just remember that basic idea, that like that example I gave you of the cities and countries, and remember that and then just sort of like remember that you can lift that idea into other dimension, or into other feature sets as well. Like your features don't just have to be x and y coordinates. They can be like height, weight, uh, sex, or whatever features you want. So that's yeah,
Yes.
that's the best sort of thing I can say about kNN. Best explanation I can give about it. Okay. Right. Oh, well, I'll call it quits here then. It's been about an hour. So thanks for coming. I'll probably message you guys later and I'll find something interesting to do, and I think I'll end up posting this one up on YouTube. So you guys can have a look at it there. Where is the recording thingy? How do I stop recording? Stop share. Is recording. I want to stop.